Hi guys, welcome. Myself Venkatesh Gowda and I'm from Sri Venkateshwara College of Engineering and I'm from CSE branch. In today's video, we shall discuss about the applications of physics in computing and introductions to physics in animation. So let's start the video. So first is the introduction part. Physics in animation. So what is animation? Animation is a method of photographing successive drawings, models, or even puppets to create an illusion of movement in a sequence. Because our eyes can retain only an image for approx 1 by 10 of a second. When multiple images appear in a fast succession, the brain blends them into a single moving image. Animation is a process of displaying still images in a rapid sequence to create the illusion of movement. Next is the taxonomy of physics-based animation. At the highest level, the field of physics-based animation and simulation can roughly be subdivided into two large groups. First is the kinematics. So what is kinematics? Kinematics is the study of motion without consideration of mass or forces. Second is the dynamics. So what is dynamics? Dynamics is the study of motion taking mass and forces into consideration. Next is the frames in animation. So what are frames? A frame is a single image in a sequence of pictures. A frame contains the image to be displayed at a unique time in the animation. In general, 1 second of a video is comprised of 24 or 30 frames per second, also known as FPS. FPS in a sense, it is frames per second. The frame is a combination of the image and the time of the image when exposed to the view. An extract of frames in a row makes the animation. Next is the frames per second. Frame rate is the measurement of how quickly a number of frames appear within a second, which is why it's also called frames per second, that is FPS. Motion pictures, TV broadcast, streaming video content, and even smartphones use the standard frame rate of 24 frames per second. Animation for television in Europe, Africa, the Middle East, and Australia is played at 25 frames per second. Now we'll discuss about the size and scale in animation. The size and scale of characters often play a central role in a story's plot. We often equate large characters with weight and strength, and smaller characters with agility and speed. There is a reason for this. In real life, larger people and animation do have a larger capacity for strength, while smaller creatures can move and faster than the larger counterparts. When designing characters, you can run into different situations having to do with size and scale, such as human or animal-based characters that are much larger than we see in our everyday experience. For example, superheroes, Greek gods, and monsters. Second is human or animal-based characters that are much smaller than we are accustomed to, such as fairies and elves. Third is characters that need to be noticeably larger, smaller, older, heavier, lighter, or more energetic than other characters. So here we can see the size comparison of the characters in the Marvel. Now we'll discuss about the proportion and scale in animation. Creating a larger or smaller characters is not just a matter of scaling everything about the character uniformly. To understand this, let's look at the simple cube. When you scale a cube, its volume changes much more dramatically than its surface area. Let us say each edge of the cube is 1 unit length. The area of one cube is 1 square unit, and the volume of the cube is 1 cube unit. If you double the size of the cube along each dimension, its height increases by 2 times. The surface area increases by 4 times, and its volume increases by 8 times. When the area increases by squares, as you scale the object, the volume changes by cubes. Now we shall discuss about the weight and strength in animation. Body weight is proportional to volume. The abilities of your muscles and bones, however, increases by area because their abilities depend more on cross-sectional area than volume. To increase a muscle or bone strength, you need to increase its cross-sectional area. To double a muscle strength, for example, you would multiply its width by root 2. To triple the strength, multiply the width by root 3. Since strength increases by squares and weight increases by cubes, the proportion of a character's weight that it can lift does not scale proportionally to its size. Let us look at an example of somewhat average human man. A 6 feet tall human being, he weighs 180 pounds and can lift 90 pounds. In other words, he can lift half of his body weight. If you scale up the body size by a factor of 2, the weight increases by a factor of 8. Such a character could then lift more weight, but since he weighs more than 8 times more than he did before, he cannot lift his arms and legs as easily as a normal man. Such a giant gains strength but loses agility. At last, we shall discuss about the force exerted by characters in animation. Forces exerted by people's bodies are rarely constant throughout an entire motion. For the purpose of animation, however, one can break the character motion into short time segments and consider each of the segments to be responding to constant net force. This will make it easier for one to calculate the timing for each individual segment. As an example, let's look at the push for a jump. The force a character exerts during the push is somewhat constant, and the timing is very short, which means less than half a second. In such a case, the timing for a constant force is an excellent starting point and in most cases will do the job as it is. A character walking and pushing around is not exerting a constant force throughout the entire sequence, but during each short part of the walk cycle, the net force could be considered to be a different constant value. Thank you.